Greetings, this is Stephen McKenzie. If you want to learn more about me, please go to the About page of my YouTube channel, or I'll leave some links in the description. This demo demonstrates a remote signal processor. It's a real-time signal monitor and mathematical analysis. I'll show you the client very quickly. The client is where all the interesting things are happening, but I will show you both sides of it. The data comes from a microcontroller. It's polling the microcontroller for voltage data, and we'll explain more about that later, but this is just a quick view. And I get the data via Ethernet. Also, I'll explain this later in the video. We have these different views of this data. So I'll show you the microcontroller code. First, a quick overview that, like I said, we're mostly focusing on the client-side signal processing. And I have other samples that show some rather complex operations done in the confined space of the microcontroller, where you have to be very careful with resources. But the client is a PC, so we have this abundance of riches. And so again, the data is sampling voltage off of the microcontroller, and then that is converted to digital and transmitted as a 128-byte packet. And so I validated the results originally with Wireshark using a MAC address filter. And then I wrote a little client app using libpcap on a Linux client. Then once the client captures the packet, it goes through various translations and processing. So briefly, on the microcontroller side, the microcontroller captures analog data through the analog to digital interface, and it translates that analog data, the ADC does, into floating point data, and then we package that floating point data into a packet, a 128-byte packet. So it's actually 32 floating points. And so you could send it to your client any way you wanted to. You could send it through UART or even semi-hosting and just cut and paste or whatever. But I'm sending it via Ethernet, and so you need the right board that supports Ethernet if you're going to do it that way. And I'll show you the one that I'm using. So this is a STM32H series, or F7. There's a bigger board with 1 meg of flash and like 600 some or 500 some SD RAM. And so it has a lot more capacity, and it does come with an Ethernet driver. And if you use the STM32 Cube MX or the Cube IDE, it will initialize the peripherals for you, default values. But otherwise, you'll need to consult documentation on how to use the driver and the steps that it takes. So for example, for the Ethernet, here we'll take a look at that. So it sets this up for you, this MX underscore ETH underscore init. And so this is the MAC address. You just take the last 2 characters and bunch them together if you want to use them a filter in Wireshark. These are the fields related to receiving, and then these are the fields related to transmitting. So this ETH underscore TX packet config is a handle, and it's also a struct that points to this type. Sorry, I didn't mean to say handle. I meant like instance type of this struct with all these fields, and here's the instance declared right here. and then it is typed def into that variable we have in my init function. And so right here, this txconfig is what we're going to initialize and copy the bytes that we want to send across the Ethernet. And this is the function that does it, transmit. Okay, so now we're looking at the packet being transmitted. It's the microcontroller's in transmission mode, broadcast mode, so it's the client app just takes one packet, but it's being sent here sort of in a loop. And this is the data right here, over here on the right, the raw float data that's been sort of decomposed into bytes. And so anyway, that's how I verify that I have the right data, is using Wireshark. Oh, and by the way, I use the MAC address, I filter it, and that you put that up here. Sorry that that's so small. I only put it in Notepad. So this is the format, this eth.src, source equal, then your MAC address in this format with the colons in between the bytes. And you put that right up here in this top filter field. So I have instructions on how to run the app in the README. You press 1 to capture the packets, and then it will give you this first screen. So at the very top of the screen, we have the packet display and the MAC address, the size and all of that. And here's the 128 bytes that make up the packet at the top. Then over here on the left, this is the normalized voltage data that's been transferred to digital on the microcontroller side, but on this side we've run it through a normalizer. Then this column 2 is what we've done once we have the floating point data, is that well, we get the raw floating point data before it's normalized to construct an array of complex numbers. And I'm using the standard C++ library, the stud complex, with a real field and an imaginary field. So that is the raw data. And what you do is you initialize the fast Fourier transfer with an interleaved array. And what I mean by that is we take the raw data here of floats, and we initialize that as the real field of the complex number, and we leave a placeholder for the imaginary number with a value of 0 float. And then the fast Fourier transfer transforms that data from time, sort of like time sampling representation, to a what they call time domain, to a frequency, like a wave file, to a frequency context. And if you want to, I have a bibliography at the end if you want to read more about that. I talk a little bit more about it on my CMSIS DSP sample. But I have all the mathematical formulas in a PDF at the root of the project, and a bibliography in the slides if you want to learn more about it. My main resources for fast Fourier transform is CLRS and this older book by Sedgwick, and I have that in the bibliography. So anyway, going back to the floating point data, and once it's transformed, when it's ran through the FFT, we get the magnitudes, and I have the formula for getting that too in the PDF. And with that, kind of a simplified way of saying that is that you get the absolute value of the real or of the greatest. And so that is fed into a priority queue, and that's the first column of this. This right window has 2 data sets. The column here on the left is the output of the priority queue, and the output on the right is the output of a graph. Now the graph nodes basically are consist of the magnitudes. But then the associations, the edges that associate the nodes, are based on the raw FFT data, and it's based on signal peaks and valleys, sort of an adjacency signal peaks and valleys. And so if you look at so it's printed out as an adjacency matrix. You'll notice that the ones, where there's an adjacency, there's a 1, and where there isn't, there's a 0. You see that it's sort of diagonal, which makes sense. They're going to be nearby. They're going to be, in terms of close to the time samplings, the peaks and valleys are going to associate with samplings nearby in locality. So it makes sense that it's a diagonal ones in this diagonal shape. So yeah, so the edges are added that way on that basis, and it's printed out that way. If you press 2, you get this matrix view. And so I just used the packet data. I wanted to learn, this is just sort of a study. It's a little bit disconnected to sampling the data, but we'll get back to sampling the data on the third screen. But this one here, I wanted to deal a bit with some multi-threading, and I wanted to learn more about matrix operations. And so at the top here, basically I broke the 128 byte packet into 2 matrices of 8 by 8, so 64 bytes each. And so the first part of the packets I put in the first matrix, and the second part of the packet I put in the second. And then this second window is matrix addition. This third window is matrix subtraction. And the fourth window is matrix multiplication. And I did some hard-coded validation before I made it dynamic, so I know that these values are reasonable. Also, the fourth window is multi-threaded, and I really didn't have to use any synchronization. I should add that all of these operations log to a file. And so there's a file, it's called, I forget, it starts with matrix underscore something, but there's a file, and it shows the results, shows the source and the results, so you can validate it. And it adds to it, so you can keep logging from run to run. So this is the third screen. You press 3, and it gives you more math. And so this top screen is kind of a wave view, a 2D wave chart for the frequency representation in the results of the fast Fourier approximation. And then using the fast Fourier results, here is a polynomial multiplication using those values. You see the I is the imaginary number. Then if you press 1, it captures the data again, and you start afresh, and you can go through and look at the different views, 2, 3, 2, 1, and it'll capture again. So some improvements would be to, it'd be real simple for me to, if one send a signal to the microcontroller telling it to send the data, you have an interrupt set up. Or another idea is to have a timer that the microcontroller sends the data for like a 10-minute window, let's say, once a day, and that you have a cron job on the client side that starts up and captures the packet and puts it out to a log file. So it's all automated. So that's just some real-world application there of monitoring your devices remotely over the internet through Ethernet on a LAN. And so that whole principle is established here. So this was a fun project, and hope you found it entertaining, and thanks for your attention.